In Season 10 of Jetlag the Game, Adam Chase completed a challenge that seems random at first with truly extraordinary accuracy. The challenge was to estimate a period of 30 minutes elapsing without looking at a timer or any regularly scheduled thing, and the challenge was successful if the timer stopped within 3 minutes at that 30-minute mark. Well, here's how Adam did.
I'm counting in my head.
Was Adam lucky, insanely skilled, or just a bit of both? Let's see if we can find out, maybe learn a thing or two about probability along the way. We'll also take a look at another challenge that featured in Jetlag Season 10 that got my math juices flowing. And how fitting that Season 10 was a season with the great Toby Hendy. But this intro is getting long, so we gotta go. So I lied, we'll get to the 30-minute challenge later. It's a little trickier to analyze without starting with something easier. So let's look at the other challenge that happened in Season 10. In Episode 3, Sam and Toby drew a challenge that required them to correctly predict the outcome of a coin toss 8 times in a row within 30 minutes. They chose not to do it, with Toby deeming it, quote,
mathematically improbable.
How improbable is it though? Let's see if we can find out. Every prediction that is made has a 50% chance of being correct, so the chance of 8 correct predictions in a row is simply a half times a half times a half and so on, 8 times, which is 1 in 256. But that's not the whole story. Remember that if an incorrect prediction is made at any time, they have to start over. So just multiplying this out won't work. Let's try another approach. Every time that they flip the coin, it's not the coin that's changing. Rather, it's just the number of correct predictions that they have. Let's say they're currently on a run of 3 in a row, and they call the next flip to be heads. If the coin lands heads, it increases to 4. But if it's tails, they're back at 0. In this fashion, every step in time, or every coin flip, will have a value from 0 to 8 associated with it, which is simply the streak of correct predictions at that time. Something like this, where we have a random experiment repeated many times, and we care about the evolution of a greater system over time, is what we tend to call a random process. And one class of those that works well for this problem is the Markov chain. Now, with all the buzz around language models, you might have heard of Markov chains before, but essentially, there's some kind of random process that follows what is known as the Markov property. Given where you are now, what happens in the future is independent of how you got here. To translate that into this coin flipping problem, the coin has no memory of its history. If your streak of predictions is some value, it doesn't matter how many right or wrong predictions you had before. This generally comes with strong assumptions of independence, which we are going to take for our coin flips, but remember that it's never a guarantee. The building blocks of a Markov chain are the states and the transitions. The states are all the possible values that your system can take on, and at every step in time, you are moving between 2 different states, and that is called transitioning. And yes, you can transition back onto yourself. Every transition has a fixed probability, which comes from the Markov property, in that it doesn't matter how you got to your current state, what matters is what comes next. There's also usually an initial distribution, which tells you how likely you are to start at a given state, because you obviously have to start somewhere, but for our purposes, we will always have one initial state. The distribution will just be 1 somewhere and 0 everywhere else. And that's all you really need to know for now. First, let's establish what the states are. This is pretty simple. It's just the number of correct predictions in a row that we currently have, so it'd be the integers from 0 to 8. If we predict correctly, we transition forward to the next state. But if our prediction is incorrect, then we go back to 0. Every single arrow has probability 1/2 to symbolize the equal outcomes of flipping a coin, except for the arrow at 8, because when we get to that state, the game is over, so the only place you can transition is back to yourself. So now we have our chain. What do we do next? Remember that our goal is to work out the success rate of this challenge, but that relies on things like knowing how long it takes to flip a coin, so for now let's just focus on the number of flips. We can simulate the challenge, and we will later, but for now, it is fairly straightforward to work out the amount of flips needed to win the game, at least on average. There's this concept in Markov chains called the hitting time, which is simply the expected amount of time needed to hit a certain state for the first time, given that you start at some other state. Let's denote a variable tau sub I as the expected time to hit state 8, given that you start at state I. We'll ultimately want to find tau 0, but it would be easier to start at the end and work backwards. So then, what is tau 8? Well, it's the expected amount of time to get from state 8 to state 8, and you're already there, so it's just 0. What about tau 7? For that, let's look at all the ways you can transition out of state 7. You can either go back to 0 with 1/2 probability, or advance to 8, also with 1/2 probability. Remember that hitting time is supposed to be an average, So our answer will be a weighted sum of all the possible outcomes weighed by their probabilities. So we have a half times tau 0 plus a half times tau 8. We know what tau 8 is, it's 0. So we can simplify this down to just 1/2 tau 0. But we also have to add 1 because we have to count the amount of time that we spend inside of state 7, which is just 1. And now we have an expression for tau 7 in terms of tau 0. Let's do tau 6 now in a similar fashion. From 6 you can either go to 0 or 7, each with 1/2 probability. And we know what tau 7 is, so we can plug that in and simplify, and also make sure to add 1 at the end, and we get a new expression. Doing this all the way down until we have something for tau 1 in terms of tau 0 will get us very close. Now we need one more equation, which is going to be tau 0 in terms of tau 1. And now we have two equations with the same two unknowns. This is just a system of equations that you can solve whatever way you want, and you'll find that tau 0 was 510. So in other words, on average, that's how many flips it will take to complete the challenge. This will give us a nice benchmark for when we do our simulations. And speaking of that, here are the results of 100,000 attempts of this challenge, and the number of flips it took to reach 8 in each attempt. You can see from the shape of the bars that the distribution does sort of decay as we go on, with an earlier peak at around 100, even though the average value is closer to 500. You might call this a right-skewed distribution because much of the data is located off to the right. But now we need to decide how many flips per second Sam and Toby can do. If we say it's 3, for example, that means there are 600 flips in 30 minutes. Let's select all the bars up to and including 600, and if we take the total area of those bars, we find that the challenge is successful 69% of the time. Nice. But maybe 3 seconds is too fast. If we say 4 seconds instead, we now go down a little bit, but we're still above 50%. So I don't think this challenge is mathematically improbable, Toby. I mean, I'm sure she could have worked that out herself if she took the time to actually solve it and stuff. She is the GOAT after all. Incidentally, in Season 11, Episode 1, Adam, now competing on his own, drew a similar challenge in which he had an unlimited amount of time to flip 7 heads in a row. But this time he couldn't just skip the challenge, he had to do it. And in a balancing act ordained probably by Dave Wiskus, Adam would end up getting extremely unlucky in this challenge to counteract how extremely lucky he was in the 30-minute challenge from Australia. In 694 flips, he would not get 7 heads in a row and gave up, banning him from making progress in the game for 30 minutes. How unlucky was he? Well, we just solved this problem with 8 coins, so let's try it again for 7. We can use the same Markov chain setup as before, just with one less state. And the hitting time here works out at 254, which as you can tell is way less than what Adam got of 694. When we turn to simulation, this is exacerbated even more, as in my 100,000 attempts, only around 6% had over 690 flips. So as you can see, Adam did get pretty unlucky here. In stats, you might call something like this a p-value analysis, where the p-value is the probability of seeing something more extreme than what you observed. But I'm not about to speculate that Adam's coin was rigged. He probably just got unlucky. But there is one interesting thing that happened that people were discussing in the jet lag community. You'll notice that Adam actually got to 6 in a row 3 times, and every time he did, he stopped what he was doing to set it up nicely for the camera when he would hopefully get that 7th head. On all 3 occasions though, he didn't get the head. Now that's not that unlikely, it's a 1 in 8 chance of that happening, but there was this sense that had Adam kept his rhythm and not stopped, perhaps he could have landed the head once. Personally, I'm not too sure, and I'm willing to just choke it down to bad luck, but it is a thought. You know, sometimes production value does get in the way of challenges being complete fast, which you might not entirely like, but this is TV after all. You've got to entertain a little bit. So now turning to the 30 walk challenge. How did Adam complete it? Well, he realized that his walking was rather rhythmic, and figured that he could use that to measure the passage of time. He did a small test and worked out that he walked an average of 1.84 steps a second. Well, at least rounded to 2 decimal places. Let's just take our step rate as a perfect 1.84 and extrapolating that to a period of 30 minutes or 1800 seconds, Adam would need to walk exactly 3,312 steps. One thing you might immediately think is that it would take a ridiculous amount of coordination to maintain that same pace for the entire walk. And that's true. So I came up with a simple model to depict someone who might be doing this walk. Let's say that your rate starts at a perfect 1.84. After all, Adam only told Ben to start the timer once he was in a good rhythm. So here's the model. Every few steps, there's a 50% chance you keep your current pace, a 25% chance that you speed up a little bit, so your rate goes up by 0.01, and a 25% chance that you slow down a bit, decreasing your rate by 0.01. This model is far from perfect, but we can get a lot out of it. Crucially, in that it's set up nicely for a Markov chain analysis, where you start at the 1.84 state, and every time you take 8 steps, you incur a transition. You have a 1/2 probability of self-transitioning, a 1/4 probability of going right, and a 1/4 probability of going left. Now, Markov chains are really cool and all, but the real appeal of them is analyzing what happens in the long run. If you move through the chain for an arbitrarily large amount of time, where would you expect to end up? Sadly, for this particular type of Markov chain, the long run behavior is a little bit tricky to analyze, at least for a video that aims to be introductory and fairly short. So let's do the oldest trick in the book, writing some code and simulating. So I simulated Adam's walk 100,000 times. The step rate always started at 1.84, and then it followed the Markov chain model that we just saw. As you can see, things are pretty normally distributed, just as you'd expect, though there is a slight skew because even though the step rate is linear, when you translate that into the amount of time to reach a certain number of steps, then the rate is no longer linear. But anyway, as you can see, it seems like this challenge is pretty foolproof for getting within a 3-minute range of 30 minutes. Around 97% of simulations were able to fall in that range, according to this model. If we change it to just a 1-minute tolerance, for example, the rate drops to 53%, which is still fairly good. Does this mean that the challenge was too easy? I wouldn't say so. It did take a little bit of ingenuity on Adam's part to come up with this method, but perhaps he had that prepared long before the show started when he was actually making the challenges in the game design stage, but it's not worth speculating. So yeah, that was 2 jet lag challenges analyzed using probability. There's a couple more that might pique your interest. For example, the challenge in episode 2 of season 10, where they had to estimate the number of customers at a market. That reminds me of something called the Poisson process, which I might make a whole video about later, but it's a little tricky to explain in a short amount of time. But yeah, enjoy season 12 of Jet Lag. And I'll see you in 5 months when I upload again.